12. A periodic motion. 12.1 Introduction. Earlier chapters explained that matter in motion has kinetic energy and described the way that that energy is transferred. When energy is transferred between systems, work is done by one system on another. Work may be accomplished in two ways. A contact force acts directly, like a baseball bat's hitting a ball. A field force acts without touch, like a magnet's attracting a paperclip. Work can also be done on individual particles through collisions or in response to field forces. Linear, one-time motion is not the only kind of motion that does work. Work may also be done by repetitive motion, motion that occurs again and again. Vibrations and oscillations are two kinds of motion that can be repetitive or random. Vibrations are very small and rapid repetitive motions, and oscillations can be larger or slower movements. There's no distinct boundary between the two. These kinds of motions are observable at every size scale imaginable. Atoms and molecules randomly vibrate in response to thermal energy. Mosquito wings beat in rapid oscillations. You've seen the oscillations of a playground swing. Astronomers have observed ripples in stellar dust, light years in width. This chapter is particularly concerned with motion that repeats at a constant rate, called periodic motion. Some kinds of periodic motion require matter, while other kinds do not. In matter, periodic motion occurs when its energy alternates repetitively between mechanical potential energy and kinetic energy. One example of this periodic energy exchange is a clock pendulum. The properties of periodic motion apply to many different areas of physics, especially sound and light, which are the topics of chapters 13 to 15. Thus, it is important to understand how systems experience periodic motion and how that motion can transfer energy from one place to another. 12.2. Describing periodic motion. Position. What does periodic motion look like? An oscillating system such as a clock pendulum swings back and forth repeatedly. The pendulum is at its rest position when it hangs straight down. If you pull the pendulum to the side and then release it, it swings through its rest position until the pendulum's bob, its weight, is at an equal height on the opposite side. The pendulum stops for an instant, then swings the other way. This motion continues repeatedly and indefinitely if no outside forces stop it. Similarly, if you pull a laboratory mass hanging from a spring down from its rest position and release it, the weight and spring bounce up. The elastic potential energy, EPE, in the spring is converted to kinetic energy. The mass then rises to its maximum height above its rest position and stops momentarily. The kinetic energy of its motion is converted into gravitational potential energy, GPE. The mass then drops down to a point below the rest position. Gravitational potential energy is converted back into kinetic energy, and EPE. These oscillations repeat around the rest position of the mass and spring. You can see faster vibrations if you hold a plastic ruler over the edge of your desk and thrum it so that it vibrates. It vibrates so quickly that you can't follow its motion with your eye, but you can see that it bends above and below its rest position. The maximum distance that a system moves from the rest position during each oscillation is called the amplitude of the oscillation. The system swings to its amplitude distance at opposite sides of the rest position. Period. The most important property of periodic motion is its fixed rhythm. Each repeated motion or cycle takes the same amount of time. The word cycle comes from the Greek word for circle. If you repeatedly trace a circle with your finger, it travels the same path over and over. Cyclic motions include the spinning of a wheel, the orbital motion of a planet, and the swing of a pendulum. In fact, all periodic motions can be modeled by similar equations based on circular motion. Though constant circular motion is a general type of periodic motion, this chapter focuses specifically on oscillations and vibrations. The time it takes to complete one cycle of a system is its period, T. Physicists measure the period of vibrations and oscillations in seconds, S, the base SI unit for time. For example, if the back and forth motion of a playground swing takes 2 seconds, we express the swing's period as t equals 2 seconds. Frequency. The rate at which cycles repeat is called the frequency, F, of periodic motion. Frequency is measured in cycles per second, or hertz. For example, alternating current, AC, in the United States changes direction twice each cycle, 60 times per second. So its frequency is 60 hertz. Frequency can also be expressed in units of s to the power of -1. This is the formal mathematical way of writing cycles over s, but the word cycles is omitted since it is understood when measuring frequency. Therefore, cycles over s equals 1 over s equals s to the power of -1 equals hertz. Frequency is the inverse of period and vice versa. If the period of a water wave passing by a pier is 2 seconds, then its frequency can be figured as follows. F equals 1 over t equals 1 over 2, s equals 0.5s to the power of -1 equals 0.5 hertz. Similarly, the wings of a ruby-throated hummingbird, Archilochus colubris, beat on the average 52 times per second, 52 hertz. The period of each wing beat can be figured as follows. T equals 1 over F equals 1 over 52 hertz. T is approximately 0.019 seconds. Understanding this relationship between frequency and period will be important when you study wave motion later in this chapter. 12.3. The cause of periodic motion. Let's see what happens when you make a tight string vibrate. When the string is stationary, all forces on it are balanced. If you pull the string away from its rest position, you feel a pull as the string stretches. This pull is called the restoring force because it tends to restore the string to its rest position. The farther you pull the string away, the stronger the restoring force grows. When you release the string, the restoring force accelerates the string back toward its rest position. During the vibration cycle, the restoring force decreases to 0 as the string approaches its rest position. However, the string's speed and thus its momentum are large, so the string keeps moving past its rest position. The restoring force begins to grow in the opposite direction. It eventually stops the string and accelerates it back toward its rest position. The whole process repeats itself again and again, producing vibration in the string. When an object moves with true periodic motion, it experiences a restoring force whenever it is not at its rest position. The farther the object is from its rest position, the greater the force. The restoring force creates potential energy in the object. This potential energy may be elastic, as in the taut string or a spring, gravitational, as in a pendulum, electrical, as between charges in an electric field, or magnetic, as between magnets and iron objects. The potential energy is maximized when the object is farthest from its rest position. As the object moves toward its rest position, the restoring force converts the potential energy into kinetic energy. As the object, due to its inertia, moves away from the rest position, the restoring force converts kinetic energy back to potential energy with each oscillation. Thus, periodic motion is yet another example of the law of the conservation of energy. 12.4 Factors affecting periodic motion. Massachusetts. A vibrating system's mass affects its period. The more massive a system is, the more slowly it will vibrate, and the longer its period will be when other factors are held constant. Consider a laboratory mass attached to a spring that is connected to a wall. Assume that the mass rests on an ideal, frictionless surface. There are no net forces acting on the mass other than the spring. When you pull the mass and release it, the elastic spring force accelerates the mass through its rest position. On the other side, the spring compresses, slowing the mass until it stops. But the spring's elastic compression force accelerates the mass in the opposite direction. This motion repeats indefinitely in the absence of friction. What happens if you replace the laboratory mass with one that has more mass? The greater mass has more inertia that opposes the force of the spring. For the same force exerted by the spring, it accelerates more slowly, Newton's second law. Though the kinetic and potential energies may be the same, the maximum speed of the mass is much lower, so it takes longer to complete a single cycle. The period will be longer and the frequency will be lower. Strings on a musical instrument vary in thickness. The thicker, more massive strings vibrate more slowly than the thin strings to produce a sound with a lower frequency. Damping. Oscillations don't continue forever because all real systems are subject to friction. Energy is applied to a system to begin an oscillation. During each cycle of the system's motion, some energy is removed by air friction, internal resistance to motion, or friction with other objects. This energy is converted to thermal energy, lowering the energy available to move the system. The system's amplitude decreases, though the period remains relatively unchanged. Eventually, oscillations become so small that the system stops moving. The effect of friction on periodic motion is called damping. Damping is desirable in most oscillating systems. Without natural or artificial damping, vibrations in objects would just continue without stopping. The ground would never stop shaking after an earthquake. A plucked string would continue vibrating. Most musical instruments would sound odd if their notes were not rapidly damped. A car's shock absorber is designed to maximize damping so that, after going over a bump, the car doesn't keep bouncing. Damping in an oscillating system is unwanted when a constant amplitude is important, such as in mechanical clocks or playground swings. To overcome damping, some source of energy periodically provides a boost to sustain the amplitude. To continue swinging, you have to pull on the chains or have someone push you. Mechanical clocks use suspended weights, springs, or electromagnets powered by batteries to boost each cycle. Resonance. The opposite of damping is resonance. All objects that can oscillate have a natural frequency. Resonance occurs when an outside source adds energy to an oscillating object at its natural frequency. The amount of energy exceeds that which is needed to overcome natural damping in the system. This makes the oscillation amplitude increase. Eventually, either the structure of the object limits the amplitude or the object flies apart. You may be familiar with some examples of resonance. A person pushing a child in a playground swing exerts a force on the downward side of the swing cycle, allowing the swing to go higher on the upward side. With each push, the swing goes higher. In another example, the annoying buzzing you may hear in your car, especially at high speeds, is generated by resonance in car parts. An imbalance in a wheel or the road causes the whole car, including objects in the car, to vibrate. The frequency of the vibrations depends on the speed of the wheels. Only specific speeds generate resonant frequencies. On the other hand, horns and other musical instruments are designed to resonate to produce rich musical tones.